So the following slides, we're going to go through those well-known and often used outlier detection methods, going through those one by one, one type by one type. So statistical approach, basically we assume, it's called model-based approach because we assume there is a distribution, there is a generative model fitting the given data set. Then we can use that model to predict in what probability that object could occur. And then objects in low probability region of the model can be identified as outliers. In statistical based methods, we can have parametric methods or non-parametric methods. Parametric methods often assume there is a distribution governed by a set of parameters. For example, for Gaussian, we have the mean, we have the standard deviation. So we can use the probability density function to compute the probability of certain observations. And therefore, observations with low probability of occurring can be outliers, can be labeled as outliers. Non-parametric method, although we don't have a distribution, but we have some other models, some other parameters that can help us to identify those outliers. For example, histogram that we learned a long time ago, that can be used, and kernel density estimation that we learned today. Even we don't know. We're not, there is not a one Gaussian governs the distribution. We can estimate using just a standard Gaussian, put them on top of data points and estimate a density function and use that to predict the probability of certain points to occur. So the first concrete method that we're going to introduce is what we learned before you take this class. I'm sure you all know that. You all know this, that in a normal distribution, if the data appears 3 sigma away, then it's probably an outlier. So this works for univariate data. If your data has only one attribute, it's easy for you to identify outliers. If your threshold is like less than 3% of chance for the data points to occur. All those mathematics is just to prove that the mean and the standard deviation that we can estimate from the samples is the best estimate of the true mean and the standard deviation. I don't think that matters much here for this class, so we don't have to go through those. The book actually have very detailed descriptions. Another univariate outlier detection method is the classic Grubbs test. Here, again, it's a univariate. It assumes that data is normally distributed, and for Grubbs to have its power as designed, our data sample size need to be greater than 6. The Grubbs test has a null hypothesis of data has no outlier, and its alternative hypothesis is the extreme value, whether it's minimum or maximum, that extreme value is an outlier. When we use extreme value, we're implying that we're doing a two-tailed test. If we use minimum or maximum separately, we're imply that we're doing a one-tailed test. And the Grubbs works for both ways. So the test statistics is a z-score. I guess we're all familiar with this. For two-tailed, your z-score is this. For one-tailed, minimum and maximum, your z-score is this. If z-score is greater than this computed value, then X is the outlier. So this is a t-distribution. So n minus 2 is the degree of freedom. And this 2n here indicates it's a two-tailed test. So you will go to the t-distribution table, find this degree of freedom and your test significance, alpha, and find in the two-tails table the t-value. Compute that and compare this to your z-score and see if z is greater than this value. If z is greater than, then this extreme value is the outlier. Then you remove this outlier from your data set and test again to find a second outlier. That's how Grubbs is used in terms of outlier detection. If here your z is one-tailed, then you simply go and look up, find the one-tailed t-score to compute this value. Okay. Then we talk about two statistical methods to detect outliers in univariate data. What about multivariate data? There is also a way to do that. So the general idea, one way to do that is to transform the univariate outlier detection task into a univariate outlier detection problem. So now we have n-dimensional data, right? So we basically are testing, we compute, the method one here says to compute Mahalanobis distance. Mahalanobis distance measures the distance between a point to a distribution. So how different this point is from this distribution. So here the example shows two-dimensional data. The Mahalanobis distance is defined as such. It's a generalized form of Euclidean distance. We can see this O bar is the mean vector, and O is one observation. This observation to, let's see, this is O to the entire distribution is the square root of this, okay? And S is the covariant matrix. If these two dimensions are completely independent of each other, then this S is going to be an identical matrix. Therefore, this equation becomes a Euclidean distance. And so we basically converted our multivariate outlier detection problem to univariate, because now we have a set of distance. So every data point has a distance to this entire distribution. And this Mahalanobis distance follows a chi-square distribution with D is dimensional data, with D degree of freedom. Then you can use the QQ plot to plot your distance against a chi-square distribution to see whether the QQ plot forms a straight line. If not, then those dots that are on a line going to be are considered outliers. Similarly, we can use chi-square statistics that you can compute the expected value so the expected value would be the mean of the I dimension along all objects. And for every dimension, you compute that to see how far away this object I is from the expected value. The greater of the chi-square, the object has a higher chance to be an outlier. You can order your chi-square statistics and take the top X as the outlier. We could also use mixture of parametric distributions. This has to do with the EM algorithm. So earlier we are assuming that all data are generated by one normal distribution, that obviously is not the case. Your data may contain data points that's generated by different normal distributions, for example. If that's the case, then we can use the EM algorithm to find I'll step back a bit to say that in this method, what we did is very much like what we did in density estimation. Here we assume the normal data is generated by two normal distributions, and we can use EM algorithm to actually learn the parameters from the data. So EM stands, I'm going to just generally introduce EM, and you can look at the videos that I linked there to see the details. So the EM algorithm is designed to you have to tell EM how many distributions are in the data set. So let's see 2. And the EM going to give in the data set using iteratively two steps to find those parameters. It will start with random parameters for this 2 distribution. Then it will assign the data points to those 2 distributions and adjust this point iteratively until those 2 sets of points are all assigned to. This is the E stands for expectation and M stands for maximization. Through these 2 iterative steps, we first use the starting with the arbitrary numbers, random numbers. We compute the probability of every data point to one of the 2 distributions, that's expectation. And then using the data, compute the new mu and sigma, again, that's maximization. And so iteratively through those steps, 2 steps, we settled and eventually converge on the parameters that we want to learn. So this EM algorithm can help us if we know how many distributions are involved. Given a set of training examples, the algorithm can learn the set of parameters that we need for each of the distribution. Once we have those distributions, we can, just like what we did with density distribution, density estimation, we can add them up to get the mixture of the 2 distribution. And then we can compute the probability for this data observation to be generated by these 2 observations. And then data points with very low probability will be considered outliers. Questions? Okay. Non-parametric method. So here, we're going to revisit our old friend histogram, where we can actually remember histogram. We divide this, we can use whether either equal depth or equal width method to divide the data into intervals. And the histogram computes the density for this chunk versus this chunk. If your data points falling into one interval that has a very low probability, then that data point may be considered an outlier. So using histogram has the difficulty of how do we know how to set the bin size. If we have too small a bin size, then the normal objects may end up in the empty or rare bins. This results in false positive. If we have too large the bin size, we could run into false negative examples. Alternative to the fixed width histogram is to just do density estimation like we did before. I think somebody wants to ask a question. Is there a question here? No? Okay. So we already, I'm not going to go through this, but this probably going to help you with one of your assignment. The basic idea is the density for you were using histogram to detect outliers, density of an equal width, equal depth. Histogram going to have a low density for the beam that has outliers. This going to probably, if you need help, maybe you already know this very clearly, so that wouldn't be necessary. But if you had a question about that assignment homework, it's maybe helpful for you to come and look at this slide. This we already just talked about right earlier. Using the idea is just to finding the dent, the valleys, the areas.